You're doing well. Good girl.
Section 4.9 has to do with reducing a simple distributed loading. So far what we've done is we've looked at point loads. And point loads are, let's say you have a structure, a beam, and you apply a load at a point. Okay, so that's a point load. For distributed load, this is considered to be a simple loading where we have a structure, and let's say now it varies across its length. So these are all individual forces continuous across this beam. So we'll call this Fi. And situations where we might find such distributed loading or this type of simple loading would be perhaps a table, right? So an example would be, let's say you have a table and you have some boxes laying on top of it, and each box may weigh differently, maybe of different size. So our model for this particular loading would look something like this, where it's a constant load here, and then it goes down, and then it goes back up again, something like that. So since this was a table, it had some kind of width b along some length x. So we can actually think of these distributed loading causing a pressure on top of the table. So let's label this axis as pressure, and we'll give it a variable p and the units of Newton per meter squared. And furthermore, we can just elaborate that the pressure is a function of x, which is given by force at each x at some infinitesimal area dA. So we're going to simplify this a little further. We're going to just study structures that have perhaps a constant depth. So instead of looking at pressure, what we can do is just look at the loading function, or the load. So we can simplify the above to some kind of loading function, a simple loading function. Simple loading function. And we'll call this W of x. And it'll have the units of Newton per meter, because we are actually not taking into account the width of the table or this dimension b. So W of x will now be defined as this P of x times b. So since this was Newton per meter squared, and that is a meter in terms of units, the units for W of x would be Newton per meter. So again, that loading function would look the same as before, but the unit is now in Newton per meter. So the objective of this section is to be able to take this distributed loading, this simple loading function, and reduce it down to a single force, right? So we want to know, how can I represent this distributed loading into a single resultant force that acts on that length of the table. So objective 1 for this section is that if we're given this distributed loading function W of x, we want to find the resultant force Fr. So suppose you have a loading function that looks something like this, that acts on a beam, and we'll draw the individual forces like this. And of course this is infinite across the beam here, but just to illustrate that there are these vertical forces, I'll just draw it that way. And this line is given by a function W of x. That means we have an equation for it. And we'll say that's at 0. And we'll say that this is at some distance x1. What we want to do is replace this complicated loading function into a single force Fr that acts somewhere at a distance, and we'll just call it x bar for now. To do this, you use this equation. The resultant force is equal to 0 to x1, and you take this equation and you just integrate it. So you use this only if you know W of x. And you can tell that this equation is actually just the area under the curve, under the loading function curve. Objective 2. So given W of x, find location of Fr. That is, we need to know where x bar is equal to. To do that, you're going to use this equation, and I'll now define what x bar means. It is the centroid of the loading function. Loading function area. So if we know W of x, what we do is we take the integral from 0 to x1, write x all the time, and write your loading function W of x and integrate it with respect to dx, divided by 0 to x1 times W of x dx. So remember, we said that this integral right here was actually the area under the loading function curve. So that's this right here. So I can rewrite this or re-express this as 0 to x1 x dA divided by this, which again is integral of dA from 0 to x1. But we also know that this term in the denominator is actually the resultant force, so we can write it as. So here's an example to illustrate objectives 1 and 2. So suppose we're given a beam here, and it's subjected to a loading function that looks something like this. So we're given this loading function, and it has an equation of 60x squared, and it's in Newton meter, this being my x-axis, this being my W of x-axis. And they tell us also that the magnitude right there is actually 240 Newton meter. And here's 0, and it's 2 meters in length. What they would like for us to find is the resultant force and the location of where that force should be applied. So they want to know where the centroid is. So solution. Since we are given W of x, what we'll do is we'll use this equation. So FR is the integral of this loading function with respect to x, integrated from 0 to 2 meters, which is just the area under that curve, and that would equal to 0 to 2 meters times 60x squared dx. The resultant force is 60x cubed over 3 evaluated from 0 to 2 meters, which would be 60 over 3 times 2 cubed minus 0 cubed, and the resultant would be 160 newtons going downwards. So we found that. The next part is to find the centroid. So the centroid of the loading curve can be found by using this equation. So x bar is equal to the integral from 0 to 2 meters, x times that loading function w of x dx, all divided by 0 to 2 meters of that loading function dx. We just substitute that equation, 0 to 2 meters, x times 60x squared dx, all divided by 0 to 2 meters, 60x squared dx. Again, this is just the same as that, so we're going to replace the bottom integral with a value of 160 newtons. So x bar is equal to 0 to 2 meters, 60x cubed dx, all divided by 160 newtons, 60x to the fourth, divide by 4, all divided by 160, and evaluated from 0 to 2 meters, and the unit is in meters. X bar is equal to 1.5 meters. What this means is that this resultant force, if it acts 1.5 meters from the origin, like this, so if this is 0, 2 meters, 1.5 meters would be about there, I would have a resultant force of 160 newtons. What this means is that if I were to take a video, let's say of this particular beam subjected to this load, and I take a separate video and take the deflection of this particular beam subjected to 160 newtons, 1.5 meters away from the left end, it would deflect the same way. Therefore, these two systems are equivalent. What we want to do now is analyze a system where the distributed loading W of x is not given. So consider a beam that's shown right here, and let's say it has a length of 6 meters, where this is 4.5 meters and this is 1.5 meters. And the distributed loading looks something like this. Okay, so this is W of x, and it's in newtons per meter. And this value right here is actually 6 kilonewton per meter. And this value right here is 3 kilonewton per meter, right? So that's right there is 3 kilonewton per meter. And it's a distributed loading, so I'm just going to draw these vertical forces. So this is given, and what they would like for us to find is the resultant force and the location or the centroid where it acts. So to find the resultant force, we need to know the area under the curve. And we did this in the previous problem. But we're not given this w of x function. But this is really simple because these are basic geometric shapes. And we can find the area under the curve by just taking maybe this triangle and using 1/2 the base times height, taking this rectangle and just multiplying it by the base times height. So what we need to do is, to calculate the resultant force, I need the area of that triangle on the top, and I have to add it to the area of the rectangle. So that's simply 1/2 the base. Base would be 4.5 meters times the height. That would give me 3. And then for the rectangle, that would be 6 times 3. And that would be 6.75 plus 18. Units are in newtons. And this should add up to 24.75 newtons. So that's our resultant force. So we've got that done. Now what we need to do is calculate x bar, which is the centroid. To calculate the centroid, what we're going to do is calculate the centroid of the triangle and calculate the centroid of the rectangle. So it turns out that for triangles, the centroid can simply be found by taking the base, dividing into thirds, and taking the height, again, dividing it into thirds. And the centroid will be right at this bottom corner right there. For the rectangle, it's just simply halfway between the width and halfway between the height. So let's do this. The centroid for the triangle would be 1/3 n. So if the base is 4.5 meters, that means it would be at 1.5 meters. And if I divide this into thirds, I would have 1, 2, 3, so it'd be right here. So that would be the centroid of that triangle. Centroid of the rectangle is 3 meters in because the base is 6 meters. That would be halfway right here, so it would be right here. It's 3 meters up, so it'd be 1.5, so it would be right here, where this is 1.5 kilonewton meters, and this right here is 3 meters. So this resultant force of 6.75 acts at the centroid of the triangle, going downwards, and this 18 newtons acts at the centroid of the rectangle. So I draw this force right here. That would be F of my triangle being 6.75 newtons. And F of my rectangle is 18 newtons. But we're not done yet. What we want to do is calculate the overall centroid, meaning we have this 6-meter beam here, and we want to know where this resultant force should be applied. So it lies somewhere along here. We don't know exactly where it is. It is this dimension that we're trying to find. So this is how we go about doing it. If I have the system where I have replaced the distributed loading with two forces, it should be equivalent to this beam subjected to one resultant force. So if these two systems are equal, then to determine the centroid, we have to do the following. If I look at the system on the left and I take that to be my point A, then the sum of the moment about point A due to this force and this force should equal to the moment that this resultant force causes about that point A. So it should be moment about A due to force Fr. So let's do that. Moment of the 6.75 Newton force about point A would be a negative 1.5 meters times 6.75. It's negative because if you put your fingers along the moment arm, rotated in the direction of this F of 6.75 newtons, your thumb goes into the page, that makes it negative. Same thing for this 18 newton, the moment arm being 3 times 18 newtons, and that should equal to this moment arm, which is what we're trying to determine, times that resultant force, which we know to have a value of 24.75. And we know that this is equal to 24.75 newtons. We solve for that dimension, the centroid, and you should get 64.125 divided by 24.75, and we have a centroid of 2.59 meters. That means that this is equal to 2.59 meters. So we have found the resultant force of 24.75 that has to be located 2.59 meters from the left, such that if I were to take a video of this beam subjected to this distributed loading, it would deflect in the same manner as if this beam only being subjected to a resultant force at a location of 2.59 meters